Heavy Structure Lab. The Heavy Structure Lab is one of the advanced labs under the discipline of civil engineering. It is basically provide facilities to conduct large-scale structural testing, where most of them are destructive tests for civil engineering structural elements. You know that most of the civil engineering structures are rather big. In order to know the structural performance of a structural element, it is not possible for us to conduct testing on the actual structure. Normally what we'll do is to fabricate the specimen as per the design of the structural element and simulate the loads as per the actual situations and conduct testing in the laboratory. And in order to know the behavior of a structural element, the best way is to conduct the destructive tests. That means the specimen needs to be tested to fail, so that we obtain the maximum capacity of the specimen. Therefore, you will expect quite a large heavy structure lab, as it needs to allow for full-scale testing of the structural element. Of course, if the actual structures is too massive, it is also possible for us to reduce the scale, maybe half of the scale or 1/3 of the scale for the experimental testing, and then later use some analysis approach to work out the actual situations in equivalent. The figure here shows a typical heavy structure lab. In fact, this is already considered quite an advanced heavy structure lab. Not many universities or institutions has the luxury of having the heavy structure labs to this scale. For this kind of lab, you're going to expect big testing equipment, complex system, which is going to be quite costly. You require technicians who are really skillful, not only knowing how to manage the lab, but also knowing how to operate those equipments. The entire lab needs to be managed properly. The experiment needs to be conducted carefully, as it involves costs. Any mistake during the experiment will directly lead to the implications in terms of the cost, as well as possibility lead to the hazard or safety concerns. It is one of the lab has high risk of safety issue. What you see from the diagram here, there are quite a number of systems within the heavy structure lab. Each are taking their functions in facilitating the experimental works. Mostly the focus of the study related to the heavy structure lab, it is to the structural side of civil engineering. We can see there is overhead crane, strong wall, portal frame, there will be scaffolding, actuators, specimens, strong floor, forklift, other testing jigs, and etc. Most of the university offering program for civil engineering has a heavy structure lab. Only the scale may vary quite significantly depending on amount of investment the university would like to put into in this particular field. The most basic heavy structure lab, we have a strong floor system, a portal frame, and a hydraulic jack system. Now let us look at every single components of the heavy structure lab as well as their functions. There will be a strong floor system which allows fastening of the portal frame system for testing. You know that heavy structure lab is meant to test full-scale specimen in simulating the actual situations. That means you're going to fabricate the specimen and test it with load. You will need a portal frame to withstand the loads acting on the specimen, and this load needs to be transferred but the load cannot be transferred to the structures of the heavy structure lab building. This can cause damage to the entire building structure, and most of the buildings for the heavy structure lab are not designed to withstand this kind of load. Therefore, there will be a need of the strong floor system used to fasten this portal frame. Whichever the loads being applied onto the specimen through the hydraulic jack system or through the actuator system, it will be transferred to the portal frame and then subsequently to the strong floor. All the loads and stress need to be fully absorbed by the strong floor system. It should not allow any force to be transferred to the building system of that particular lab. That means the strong floor needs to be designed to carry very high load without failure and not to transfer any load imposed onto the specimen to the building structures of the lab. This made possible of the specimen being tested with the load capacity beyond those that can resist by the building structures of the heavy structure lab. You can take this photo as a reference. What you see here, there is a portal frame here. Attached to the portal frame, there is an actuator system. This actuator system is used to induce load onto the specimen, which is normally placed under the actuator system. And this entire portal frame is being anchored to the strong floor. When the actuator applies load onto the specimen, this causes the loads being transferred to the portal frame, and then through the columns of the portal frame, the load is distributed to the strong floor. As long as the strong floor can last the load, there won't be any implications to the building structures of that particular lab. This is the main functions of the strong floor. The strong floor provides resistance to the vertical and horizontal load exerted by the actuator or hydraulic jack system during testing, depending on the setup of the portal frame. The idea here is not to allow any loads to be distributed to the building structure. You see all the loads are being applied onto the specimen, including the resistance provided by the support, which is also withstood by the strong floor. This creates a loop of the load, and the stress will eventually meet within the strong floor. As far as the strong floor concerned, there will be reactions to the specimen, as well as the reactions for the portal frame. Under this setup of the portal frame, the major loads applied onto the strong floor, it will be mainly due to the compressions below the specimen, as well as the pulling force at the support of the portal frame. If you need to simulate the horizontal load, particularly when you use your hydraulic jack system applying horizontal load onto the specimen, this horizontal load needs to be resisted by the strong floor, also through the base of the portal frame, and the strong floor will need to resist the horizontal load. The next question is, how does a strong floor look like? There will be a series of fastening points, which is spaced at a constant interval, either half a meter interval or 1 meter interval. Those fastening points are meant to anchor with the portal frame. The portal frame will be installed onto the strong floor through this anchoring point. Whichever loads applied onto the strong floor through the portal frame, it will be distributed through this anchoring point. With that, your anchoring point will need to resist the vertical pull-out force and also horizontal shear force. And this anchoring point must not fail throughout the testing of the specimen. The next question is, what makes the strong floor? It is typically a slab, reinforced concrete slab, which is designed to withstand high load with a specific capacity such as 1500 kN or 2000 kN and etc. And there will be fastening point arranged in the grid for the installations of the portal frame as well as the testing jig. The testing jigs are some custom-made instruments that helps to conduct the experimental testing, such as providing the support to the specimens, providing mechanism to restrain the portal frame, to hold the actuator system, or to simulate some kinds of load during the experiments. This will be very much dependent on the type of the loads that you would like to simulate and how you would like to conduct it. These are the considerations. You will need to consider the load capacity of the strong flow. Normally there will be specifications for the pull-out force and then the horizontal force. You can get those informations from the lab technicians. Should you want to conduct full-scale testing, you need to do some basic calculations. Ensure that the load capacity of the strong flow is not exceeded. In fact, under normal circumstances, they have all this considered during the setup of the heavy structure lab. Normally, the actuator system has their own capacity. Let's say the maximum capacity here is 500 kN or 650 kN. Normally, the strong flow will have capacity much greater than this. However, it is always a good practice of you to cross-check the capacity of the strong flow before you want to use it. You will need to check the spacing for the fastening points. Some may be half a meter spacing, some may be 1 meter spacing. This is especially required when you need to design your own portal frame in order to conduct the respective testing. You know that the idea of portal frame, it is like assembly the structural element, something like IBS system or something like Lego system, which you assemble them together in order to resist the load acting onto the specimen. And the entire system here, both the portal frame, actuator system, as well as the strong flow, must not fail before the specimen fails. You need to make sure your specimen's capacity, at least estimated capacity, must be less than the entire system in the heavy structure lab. You will need to consider the natural frequency also. You know every element have their own natural frequency. This is especially important when you need to simulate cyclic load. That means you want to simulate the load in continuous fluctuations. Normally happens in the modes of oscillations, something like trying to simulate the seismic actions or to test the fatigue response of the specimens. You know that natural frequency cannot be equals to the frequency you would like to test the load. This is to prevent the amplitude to build out, which eventually leads to the damage of the structures. And this can be a significant disaster. And normally during the setup of the heavy structure lab, they have those incorporated in the considerations that definitely they will not go and buy any actuator having the capacity equals or greater than the natural frequency of the strong flow. For typical civil engineering testing, we barely use the load frequency more than 20 Hz. The meanings of 20 Hz here is within 1 second, there are 20 oscillations of the loops. This one is already considered quite fast. However, it is always a good practice for you to check with the lab technicians what is the natural frequency in the case that you would like to conduct the cyclic load or fatigue load, simulating the seismic response of the structure or the fatigue response of the structures. Also, you will need to consider for the working mechanism as well as the installation procedures and requirements. This is something big, require advanced knowledge, require technical advice from the technicians, as well as the lab managers, and everything needs to be properly designed to avoid unnecessary damage or the occurrence of any hazard in the laboratory. These are a few working mechanisms for the strong flow. There could be more. The common ones are these three. The first one is the top-bottom bolted system. That means you install the portal frame. This is the base of the portal frame. There will be access underneath the strong flow. This is the strong flow. And then the fastening mechanism here, it will be fastening at both top and bottom of the portal frame. The second mechanism is similar, except that you impose post-tensioning force onto the anchor bolt here. This provides a better grip between the strong floor and the portal frame. If you cannot imagine this kind of system, you may look at the diagram here as a typical top and bottom strong floor system. There will be access underneath the strong floor, and your anchor bolt being installed at the fastening point will need to be properly bolted underneath the strong floor. It requires the cooperations between the top and the bottom of the strong floor. There is another system here, which is known as the interlocking post-tension bolted system. The idea here is there is no access underneath the strong floor. However, there will be a built-in interlocking mechanism in the strong floor where you're going to put into the anchoring bolt, rotate it so that it interlocks with the mechanism, and then conduct this post-tensioning force in order to fasten the bolt. All these mechanisms are meant to fasten the portal frame to the strong floor so that the force are effectively being delivered to the strong floor, as well as to ensure the stability of the portal frame. Normally, you will do this together with the lab technicians who have experience. I would recommend to you, don't do it yourself. This requires good supervisions. Any mistake during the installations of the strong floor can lead to disaster. These are several considerations that you need to take into account related to the strong floor system, especially when you need to set up a portal frame. First, when you want to install the portal frame, you need to check the fastening route as well as the bolting system carefully to see if there is any visible defects. It is especially when the post-tensioning force is involved. You cannot allow any cracks within the fastening rod, as post-tensioning force applied to the rod here will constantly stress the bolt, and those minor damage may eventually deteriorate and leads to the failure of the entire system. Always check the good conditions of the rod. You will need to check the accuracy of the fastening point grid. We mentioned that the spacing of the fastening point is fixed. However, not all the strong floor available in the market are properly constructed. I mean in terms of the accuracy. Some may be off by 5 mm, although the requirements will be plus minus 2 mm. If you have industrial experience, constructing a slab to that level of accuracy, which is plus minus 2 mm in the X, Y, and Z directions, that one is already very advanced, which will involve the specialists. Under normal constructions, it is very difficult to achieve up to that level of accuracy. Although many contractors would like to claim that they can do it, they do not see the difficulty of fabricating the strong floor system assuming it is just a typical slab, a typical RC slab. However, the challenge here is the accuracy of the spacing. Personally, I have observed several universities that have problem with the accuracy, and there will be some fastening point totally cannot be used due to these variations in terms of the accuracies. If you choose to use that fastening point, that means you need to do proper measurements of those, and the base of your portal frame will need to be custom made, fitting the exact positions of that fastening point. You cannot assume that the fastening point is perfectly accurate. Otherwise, you will find difficulty in terms of the installations of the portal frame. Next, you will need to ensure the fastening points are properly installed, following the standard procedures up to the required post-tensioning force, and mind the sequence of the installations, and also with close supervisions of the lab technicians in order to prevent any hazard occur in the lab. And it is always a good practice of you, after you have installed the entire portal frame as well as the actuator system, always before you start the testing, please do a routine check for the entire system. This includes the portal frame, whether it is properly installed onto the strong floor, as well as the actuator system, whether it is properly positioned and installed to the portal frame.